Okay, hi, so let's figure out how to do the electronic configuration of an atom. So in order to figure out the electronic configuration, you have to look at uh, this. You have to look at the periodic table, and then first of all, you could divide the periodic table into three subsections or four subsections for the S, P, D, and F orbitals. So let's just show a line that divides these sub these subshells in the periodic table. So, oops.
It makes editing much easier.
So this would be called the S orbital, and this would be called the P orbital, and this. So this would be called the S, and this would be called the P and D and F orbitals. So what's so in order to figure out the electron configuration, you basically figure out, since the number of columns in the periodic table tells you how much electrons there is per orbital. Since the S orbital has two columns in the periodic table, it has two electrons. It has a maximum of two electrons, and the P has six columns, so it could hold a maximum of 6 electrons, and the D could hold a maximum of 10 electrons, and the F 14. So if you know this, basically hydrogen atom, since is in the S orbital and it only has one electron, right? Since it's in the first column of the S orbital, you just write 1s1, right? 1s1 for hydrogen, and helium is also part of the S orbital. That's what I have to mention. So helium, you could just stick helium right here into the S orbital sections, and then the electronic configuration of helium, since it's in the second column of the, if you stick helium right here, it would be in the second column of the S orbital. So its electronic configuration would be 1s2. So you get the gist of it, and then for like let's pick a random element like silicon. Let's find the electronic configuration of silicon. So electronic configuration of silicon would be 1s1, since 1s2, since it fills out in the first quantum number. So let's label this 1, 2, 3, 4, 5, 6, right? So in the first quantum number, it fills out both of the two electrons. So it fills out both of the two electrons in the first quantum, because it's like way after that. And then in the second quantum, it fills out both of the two electrons in the second quantum. So it would be 2s2. And in the third quantum, it fills out all 6 electrons. So it'll be 3. Wait, no, in the second quantum still, it fills out all 6 electrons. And in the third quantum, it fills out all 2 electrons in the third quantum in the S orbital. And then it fills out only 2 electrons in the third quantum part of the P orbital. So it'll be 3p2. Okay. So this is how you figure out the electronic configuration, let's say, of an atom in the p orbital part. So, but when you get to d orbitals, you subtract the quantum number by 1 when you have an element in the d orbital. Like for example, if you have, let's figure out the electronic configuration of chromium. You would write the same exact thing, except for in here the third quantum you would write 6, since it fills out all 6 electrons, right? In the third quantum, and then in the fourth quantum it fills out all 2 electrons, and it goes back to 1, 2, 3, 4 electrons. It fills out only 4 electrons in the d orbital, in the d subshell. But then, since the d subshell, you subtract the quantum number by 1, it will be 3d 1, 2, 3, 4. It'll be 3d4. 3d4. But how do you figure out the valence electrons of this? Since 4 is the highest quantum number, this 4s2 would be in the outermost shell of the electronic configuration. So since the outermost shell has a maximum of 2 electrons, it has 2 electrons in the outermost shell, the valence electron for chromium would be 2 minus. But hold on a second. Chromium is a special kind of element in that it has a monopoly, something called a monopoly, which is since like this 3d4, like if you write the, hold on, pause.
Mr. Aziz, I have.
Okay.
Alright, Aziz. What about if see this element GE over here?
Yeah.
Would you still subtract n minus 1 for
For the
d
fourth quantum?
orbital?
Yeah,
Yes.
you would still subtract the n minus 1.
Thank
And
you.
there's only two special things, like two special cases in the transition metals part, where since the 3d4, if you write the orbitals, like the spins, since the d orbital, it has 5 boxes, 1, 2, 3. 1, 2, 3, 4, 5, and then if you write the spins, you first fill out all of the up spins, and that's basically it. And then for the 4s2, since it's the s orbital, it has only 2 boxes. Since to find the number of orbitals, you subtract 1. I mean, you divide the number of electrons by 2. So you divide the number of columns by 2, since the number of columns tell you how many electrons it is. And since each orbital has 2 electrons, each box will have a maximum of 2 spins, plus 1/2 or minus 1/2, and that's represented by ms, which could have either plus 1/2 or minus 1/2. Okay, since the 4s2 would be like this, 1 up and then 1 down, since like this box is almost full, right, but it's actually not full, if you just take one of these orbitals and then you just delete it here and then you put it here, this would be 5s1, 4s1 to 3d5. This is only a special case that happens.
Okay, show me which special cases it happens for.
Usually
Different
happens
colors.
for this column and for this column. Yeah, gold, silver, no,
Copper.
gold, yeah, whatever. Gold, aluminum, and no, copper, silver,
And gold.
yeah, whatever that. Thank you very much, and now you have a nice day. See you in the next video.